Welcome students to the 11th lecture of Control System 2. So till now we have discussed about how to represent any dynamical system using state space representation. After that we have understood that if the state space representation of a dynamical system is given, then how we can find out the transfer function from that. And then we have discussed that if a transfer function is given, and from that how we can create different model canonical representation of that. Now it is our interest to know that why the system or why this representation is called state space, because previously definition of the state space we have given, but it was not clear that why we are calling it state space. Along with that, we are interested to know that if we are giving a input to the system, then how we are going to find out the output of the system if the system is represented in state space. And also we are interested to know that how we can find out the stability of a given system if the system is represented in state space. And overall we are interested to know that how we can design controller if the system is represented in state space along with observer design. So if we want to understand all these topics, then it is required to understand some mathematical notion related to linear algebra. So today that's why we are going to start to discuss about the review of linear algebra. Certain concepts what we are going to discuss may be known to you, but again we want to recollect it, because frequently after these lectures, when we are going to discuss about the topics what I told, it is required to understand certain topics related to linear algebra. So today we are going to discuss about the field, then vector space, then vector subspace, then linear combination and spanning set. So now we are going to define the field. The field is defined in this way. A field F is an object consisting of a set of elements and two binary operation, that is addition and multiplication, such that following axioms are obeyed. That is, addition is associative, that is alpha plus beta plus gamma is equal to alpha plus beta plus gamma, where this alpha, beta, gamma are belongs to the field and and then commutative, the addition is commutative, then you take elements alpha and beta from the field, and alpha plus beta is equivalent to beta plus alpha. And also there must exist a identity element, that is 0, that is alpha plus 0. If you take any of the element from the field and if you add with the alpha 0, then you will get back the same element alpha. Also there exists inverse element, that is for all values of alpha, but any element you choose from the field alpha, there exists minus alpha, such that if you do this operation, alpha plus of minus alpha will be equal to 0. So these are the properties associated or axioms associated to the addition has to be obeyed by the set of elements in the field. And then similarly the multiplication is also associative, multiplication is also commutative, and there exists a identity element 1, and if you take any element from the field and if you multiply with 1, then you will get back to the same element alpha. And there exists a inverse element, that is for all values of alpha which is certainly not equal to 0, there must exist alpha inverse or 1 by alpha such that alpha into 1 by alpha is equal to 1. And finally, the multiplication distributes over addition, that is alpha into beta plus gamma will be alpha into beta plus alpha into gamma, and beta plus gamma into alpha will be, here alpha is missed, so it will be beta into alpha plus gamma into alpha. So now we will call the field f is an object consisting of set of elements if it is going to obey the axioms related to the addition and the multiplication. Then what would be the examples of field? Now, first of all, it is easy to see that the rational numbers satisfy all the field axioms. So rational numbers Q, the set of rational number Q is a field. In fact, verifying the field axioms for Q simply boils down to the basic arithmetic properties of the integers, that is associativity, commutativity and distributivity, and the existence of 0 and 1. Similarly, the set of real numbers R and the set of complex numbers C are the example of fields. But the integers z are not a field, since the field axiom 8 is not satisfied by z. What is axiom 8? You see, axiom 8 is telling that there exists inverse element, that is for all values of alpha there must exist 1 by alpha such that alpha into 1 by alpha is equal to 1. Means, suppose any integer, if you take suppose 2, we are taking 2, but 1 by 2 is not an integer, so that's why this property is not going to be satisfied. So that's why we can say that z, the integer, the set of integer z is not the example of field. Indeed, the only integers which have multiplicative inverses are plus minus 1. Other than that, this axiom 8 is not going to be satisfied by the set of integers, so we cannot or we can say that the integer set of integers will not qualify as a field. But the example what it is cited here, that is the rational numbers Q, real numbers R and the complex number C will be called as a field. Now we are ready to define the vector space. Now vector space or linear space, now we are going to define a vector space V comma F. It means that the vector space V over the field F is a set of vectors V and a field of scalar F, and the two binary operation, that is vector addition and the scalar multiplication, such that addition will be associative. You take two elements x and y from the vector fields, and if you do the addition operation, that is x plus y, that resultant vector doing the addition operation x plus y also will be belongs to the vector field V. So this addition operation is associative, means you take any elements x from the vector field V, you take another element y, or you can pick another element y from the vector space V, and another element another vector you choose z from the vector space V, and if you do the x plus y plus z, then it will result will be x plus y plus z. So it must be commutative, means x plus y will be equal to y plus x, and there exists a identity element 0 vector, that is 0 vector. Here you try to understand, this 0 is not the scalar 0 we have discussed in case of the field element. Okay, it is not a scalar. Here this 0 is a vector. So means what I want to tell you, that if you see the commutative element x plus y, so here from the vector, suppose we are choosing a vector x which having suppose k number of component x1 x2 like that, x of k, and we can choose another element another vector y. So this x must be belongs to vector space V, and y we are choosing another vector, that is suppose y1, y2, y of k, and definitely this y belongs to the vector space V. Now you are doing this operation x plus y can be shown that y plus x. So similarly, there exists a identity 0 vector. So sometimes it is 0 vector is indicated by theta v. So here it means that we have k number of component. Okay, k number of components are there. So if you add this 0 vector with the x vector, you will get the x vector in return. Okay, and there exists a inverse, that is for all the vector x belongs to V, there exists minus of x such that x plus of minus x resultant to a 0 vector, that is theta v. Okay, so you can verify that one, that if we have a vector x, that is x1, x2, x of k, then the minus of x, definitely minus of x1, minus of x2, minus of xk, and if you do the addition of these two vector, then you will get a theta v, that is the 0 vector. So similarly, if we will see for the scalar multiplication, that is you choose a scalar alpha from the field F, okay, and you choose any vector from the vector field V, and if you do the scalar multiplication, that is alpha into x, that also will be belong to the vector space V, and it is the scalar multiplication. You see, the scalar multiplication is associative, that is alpha into beta into x will be alpha into beta into x, and there exists a scalar 1, okay, that this one here it is representing that multiplicative and additive identities from the field. You choose one from the field, and if you multiply with a vector x, then you will get the same vector x, and you choose a 0 element from the field, and if you multiply that 0 element with the x, you are going to get the 0 vector, that is theta v, and it is also obeying the distributive laws, that is alpha plus beta into x will be alpha x plus beta into x, where x belongs to the vector v plus, but the alpha and beta is belongs to the field f. Then alpha into x plus y is equivalent to alpha x plus alpha y, where alpha belongs to the field f. So if a vector space is going to obey these axioms, okay, and or we can say that these properties, then we will call it as a vector space. Fine. So what will be the example of the vector space? So example is that the first example is the obvious one. If n greater than equal to 1, then the Rn with the usual component wise addition and scalar multiplication is a real vector space. Okay, so we will take the elements from the field real field R, and we can construct a vector with the dimension n with that real component which is chosen from the field. Then we will have a vector space, that is a real vector space Rn. Okay, that is a vector space over the field R. We usually call Rn, that is real n space. So you see, so this Rn. So now if we want to imagine that suppose R2. So R2 means we will choose the elements from the field R, okay, and it having two components in the vector field, that is that vector space, that is you can imagine pictorially that it having two axes, that is suppose suppose y and x, and we can say that this is a vector space of R2. Fine. Similarly, we can imagine that what will be the R3. So there are three three components of that vector space will be, that is R1, that is x, y, z. And in this way, if we are talking about real vector space Rn, means it having n number of components which is chosen from the field R. So that's why in the next it has been told that more generally for any field F and greater than and n greater than equal to 1, the set F of n of all n tuples, that is x1, x2, xn transpose of elements of F, can be made into a vector space over the field F in exactly the same way. That is, you can verify their whether they are closure under addition and then or not. That is, you can see that you can choose x1, x2, xn, that is a vector from Fn, and y1, y2, yn transpose, that is another vector from Fn, and if you add, the resultant vector also will be from the Fn. So and also it will be closure under scalar multiplication, that is alpha into x1, x2, xn transpose is equal to alpha x1, alpha x2, alpha xn. So if you are calling Fn is a vector space, then it should obey, or it should obey these two properties, means it should be closure under addition and it should be closure under scalar multiplication, which is equivalently to verify that addition operations and the multiplications operation which we have stated to define the vector space. Fine. So now I think you can we can go for another example. You see that which is also a vector space, that is set Pn of all polynomials with real coefficients having degree at most n is a real vector space. So this is a polynomial of x has been shown whose degree is n. So it is also can be shown that this polynomial, this generalized representation of the polynomial, is closure under addition as well as the scalar multiplication. So this is also the example of, means the Pn, set of Pn of all polynomials will qualify as a vector space. Consider the differential equation y double dot plus a y dot plus by equal to 0, where a and b are real coefficient. This is an example of a homogeneous linear second order differential equation with constant coefficient. The set of twice differentiable functions on R which satisfy one is a real vector space. Then another very good example of vector space is that let R 2 by 2 denotes the set of 2 by 2 matrices. So whenever I will tell that R 2 by 2, it means that all the 2 by 2 matrices whose elements are chosen from the real field we are indicating. If addition and scalar multiplications are defined to be standard matrix operation, then R2 by 2 is a vector space. Means all the means the set, that is R2 by 2 in which all the 2 by 2 matrices are included with real elements is a vector space with the following operations. Means it must be closure under addition and it must be closure under vector scalar multiplication. So how we are going to verify? Now suppose you choose any two vectors a and b from the vector field vector space R2 by 2. So a is chosen like this and b is chosen like this, where aij and bij are real constants. Means this aij and bij definitely from the real field R. Now if we do a plus b, then the resultant matrix also we are finding that the dimension is 2 by 2, so it is closure under addition. And whether it is closure under multiplication, scalar multiplication, yes, alpha into a, if you do, the resultant matrix is also belongs to the R2 by 2, so it is closure under scalar multiplication. So that's why this R2 by 2 is going to qualify as a vector space. So we will call it, so it is a very generalized, the concept of vector space, you can say that it is a most generalized idea where you can see that in general R m by n, the set of m by n matrices are also a vector space which standard with the standard matrix addition and the scalar multiplication. Fine. So now we will give an example which is not a vector space, then it will be clear that to whom we are not calling as a vector space. Suppose we have chosen a vector space V such that we have included in that vector space V, or the vector space V, where we have chosen all the matrices with dimension 2 by 2 and all the elements are real, such that the determinant of A not equal to 0. So we have collected that we have collected such kind of A matrices whose dimensions are 2 by 2 but whose determinant is not equal to 0. Can we call this V as a vector space, or this V will qualify as a vector space with the standard matrix addition and multiplication? So now this V is not a vector space. Now we have to see that which property is not going to be satisfied by the elements of this space V. So this is not a vector space. Why? Now it is not closed under matrix addition. How? Now both I and minus I. So I, if we will take I, that is 2 cross 2, that is 1 0 0 1. Okay, then there must exist minus I also, that is that will be minus 1 0 0 minus 1. You see, this 2 will belongs to V, V because you see, for both the cases, that is I and minus I, its determinant is not equal to 0. But if we do the I plus of minus I, which the resultant vector is 0 0 0 0, which is not belong to the vector space V, or the space V what we have indicated, because this I plus minus I, whose determinant is not equal to 0, but to qualify as a vector space, this property has to be maintained. So that's why this set of vectors, okay, is not going to qualify as a vector space. Now I think probably you can understand the definition what we have given for the state space. Why the state space name has been given. Basically, state space is nothing, it is a vector space of Rn. Fine. So now again we are going to recollect the definition we have given earlier. So what is the definition of state space? The n-dimensional space whose coordinate axes consist of the x1 axis, x2 axis, xn axis, where x1, x2, xn are the state variables, is called the state space. The state of the system can be expressed or represented by a point in the state space. What is the example we have cited at that time? If the state X is considered as an element of an n-dimensional vector space, then this vector space is also called state space. Now you can understand that why the name has been given that state space. The state of the system for time t can then be represented as a point in the n-dimensional state space. The curve of all these points in the state space of variable time t in a time interval is also known as the trajectory. So now we can see that one example has been given about the state space, that is R3. Okay, so this is the example of R3, where you can see that the three axes are representing the three states, that is x1, x2, x3, and you know that these x1, x2, x3 are the dynamic variable, means as the time is going to change, the states are going to evolve with respect to time. So now at any time t you can compute what is the state of the system, and that is representing the point in the state space. So that's why one point has been indicated here. You can see here this point is indicated, and at this point, if I want to compute the vector x, it having three components, that is x1, x2 and x3. So that's why the name has been given that state space, because it is coming from the concept of vector space. So now we will try to understand what is vector subspace. What is the definition? Let the vector space V over the field F be a linear space and W a subset of V. So now we have taken a W which is a subset of V, then W comma F means the subset W which is defined over the field F is called a subspace of V comma F if W comma F itself a vector space. So W will be subset of V, but W itself is a vector space over the field F, then only we will call W as a subspace. So how to check if something is a subspace? Now verify that W is a subset of V, thus W inherits the vector space axioms of V. Verify closure under vector addition and scalar multiplication. That is, if you choose two vectors from the subset of vector space V, that is W1 and W2, and if you take two scalars, that is alpha1 and alpha2 from the field F, then alpha1 W1 plus alpha2 W2 must belong to that subspace W. Notice that every subspace of a vector space contains the zero vector. Okay, so if it is a subspace, so zero vector must be consist by the subspace, because in fact the zero vector itself is a subspace which is called trivial subspace. Because if you take the R3, then origin itself is a subspace, you can say. So now thing is that what are the examples will be the subspace. Consider a vector space R2 of all points x comma y, where x and y will be the real components which is chosen from the field R. Okay, so now we are suppose here I'm going to draw, that is now we are going to consider R2. Okay, so suppose the R2 has been considered, and in this R2 any point if you choose it, so this is the R2, you can say. So any point in R2 will be represented by the coordinate x and y, where x and y are from R. Okay, so here you can say that x is real and y is also real, and you can mark it y and this you can mark it x. Fine. So now this is a vector space, already we have understood. Now what we are doing, that let L be a line through the origin 0. So now you can see that this is the origin, which is representing also a vector, that is 0 vector, that is 0 0. Now we have taken a line, a particular line which is passing through the origin, and we are calling it L. Okay, now we want to take all such of lines which is going to pass through the origin. Okay, so how we will write all such of lines which is going to pass through the origin. So here it is defined. Suppose that L is represented by the equation alpha x plus beta y equal to 0. So this is the equation of straight line which is passing through the origin. Fine. In other words, that L is a set of lines that is alpha x plus beta y is equal to 0, where x and y that is belongs to R2. Now you see we are in a R2, but we are talking such lines which are passing through 0, what is the dimension of L? So if it is R2, the dimension of L, so L belongs to R basically. Okay, so it is because the straight line in R2 is dimension of R. So now definitely the L is a subset of R2. That is true. L, all such line which is passing through the origin are the subset of R2. But now the question is that all such lines which are passing through origin are the subspace. To verify that one, what you have to do, now you have to verify whether it is closure under addition and scalar multiplications or not. Yes, and also the zero vector consists or not. So if you take alpha x plus beta into y is equal to 0, and if you are talking about 0 vector, then if you put that value, so alpha into 0 plus beta into 0 is equal to 0, means that set is non-empty set. And then you can see that it is going to verify, or you can see that it is closure under scalar multiplication as well as the closure under addition. So definitely this L, that is the set of lines which is passing through the origin, is definitely is a subspace of R2. Yes, the L forms a vector space over R. In fact, every line in R2 through the origin is a vector space over R. So this L is a vector space, means we can say that L definitely is the subspace of R2. Okay. Now another example we have taken, that is a plane passing through the origin is a subspace of R3. Our claim is that a plane passing through origin is a subspace of R3. In other words, W is a subset of R3 such that W where we have chosen the vector x, y, z which is belongs to R3. With that we have constructed a plane which is passing through origin, that is ax plus by plus cz equal to 0, and definitely this a, b and c are belongs to R. So now the question is that is the W, means the plane which is passing through the origin in R3, are they the subspace of R3? We have to verify. How we will verify? Now we have to, first step we have to see whether the zero vector is included or not. Suppose we will take 0 0 0, which is belongs to W, and we are observing that a into 0 plus b into 0 plus c into 0 is going to produce 0. So the W is a non-empty set. And then whether it is closure under addition or not. Yes, the closure under addition, or how we will verify? Now you see that we were choosing x1, y1, z1, one vector from W and another vector, that is x2, y2, z2 from W. So now if we will add them, we will get ax1 plus by1 plus cz1 will be equal to 0, and then ax2 plus by2 plus cz2 is equal to 0. Now if we will add them, then also we are finding that the result is 0. So it is closure under addition. And also similarly we can verify whether it is closure under scalar multiplication or not. We will choose any scalar alpha, then alpha into x1, alpha into y1, alpha into z1. If we put in the equation, then we are finding that it is also going to result 0. So means the plane which is passing through origin in R3 is qualifying as a subspace of R3. So what will be the pictorial representation? So now here I can show that one, that is for R3, how it will be, that I can show. That is you see, so we are in R3, so we can take R3 like this, that is x, y and z, and what will be the subspace of, so this is R3 and we are taking all such plane, okay, which is passing through the origin. This is the origin 0 0 0, okay. And what is the dimension of this subspace? That is definitely R2. So that is a subset of R3, and it is going to qualify the three important features, that is it includes the zero vector, it is closure under addition, and it also closure under scalar multiplication. So the all the plane which is passing through origin will qualify as a subspace of R3. So this is the concept of subspace. But if a plane which is not passing through origin, it is not the subspace of the R3, because at that time it is not going to qualify. The first, that is zero vector, will be not included. Okay, so this is the concept. Now another concept we are going to understand today, that is linear combination. What is the definition? Now suppose V comma F, we have taken a vector V over the field F is a linear space or vector space. Let S is a set where how the set S is constructed by picking the finite number of vectors from the vector space V, that is V1, V2, Vr, be a finite set of vectors in V. So any vector of the form alpha 1 V1 plus alpha 2 V2 plus alpha r Vr is called a linear combination of the vectors in S. So any vector, if we able to represent the form like this by picking the vectors from the set S, then we will say that that vector is a linear combination of the vectors in S. So as an example here, you see, we suppose we are in a vector space R3, then we have chosen two vectors u1 and u2 from R3 to construct the set S, where u1 is represented, you see, which having three elements 1, minus 1, 2, and u2 having three elements 1, 0 and 1. Now any vector, that is u 1, minus 1, 3 from the vector space V we have chosen, and which is a linear combination of the vector space in S. How? Now u can be expressed as a 2 into u1 plus minus 1 into u2, where alpha 1 is 2, alpha 2 is minus 1. So now we can say that the vector u is a linear combinations of the vectors u1 and u2 from the set S. So similar way, if we choose a vector space V with all the vectors or all the matrices with the dimension of 2 by 3, and suppose we are constructing a vectors, we are constructing a set S with the choice of A1 and A2, where A1 and A2 is given here, then any vector, suppose A we have chosen like this, and it can be shown that A can be expressed as 2 into A1 plus of minus 1 into A2. So the vector A, which is belongs to the vector space V, is a linear combinations of these two vectors A1 and A2. So this is the concept of linear combination. Now we will end with the discussion of spanning set. So the definition of the spanning set is that, suppose we have chosen a vector space V over the field F, then S is a set with n number of vectors, that is v1, v2, vn, which is chosen from the vector space V, be a subset of V. So now the S, what we have chosen by choosing the finite number of vectors from the vector space V, that is v1, v2, vn, is a subset of V, and we say S is spanning set of vector space V, or that S spans V if for every vector V from the vector space V can be written as a linear combination of the vectors in S. So once again I am repeating that we say that the spanning set S means S will be the spanning set of V. Then if we able to write that any vector V from the vector, if you choose any vector V from the vector space V, capital V, okay, and if we able to write as a linear combinations of the vector v1, v2, vn of a subset of V, that is S. Fine. So now what will be the example of the spanning set? Now here the example, suppose S is a set of E1 and E2, where E1 is 1, 0 and E2 is 0, 1, is a spanning set of R2. So if they are spanning set of R2, then what the quality it should have with these two vectors e1 and e2. Now any vector from the vector space R2 you choose, and that can be expressed as a linear combination of e1 and e2. So now any vector you choose x and y, it will be the linear combinations, that is v will be x into e1 plus y into e2. So any vector you choose from R2, that will be the linear combinations of e1 and e2. So that's why this set S, or this is subset of V, definitely is called the standard spanning set of R2. So now if we will ask that what would be the standard spanning set of R3, so definitely it will be that 1 0 0, then 0 1 0 and 0 0 1. So this will be the standard spanning set of R3, because any vector in R3 can be constructed as a linear combination of these three vectors. So that's why these three vectors will be the standard spanning set of R2. So this is the way we can define the spanning set of a vector space V. So now we will stop here, and next day we will come with other certain concept which is related to linear algebra, and which will be useful to understand some advanced topics of control system too. Thank you.